Now, Boby, except for one thing, I think we know all the other things here. Am I correct?
Del cross H, cross product we know.
Cross product we know, right? This is the cross product. This is the magnetic field intensity. This one we know, right? Electrical permittivity. And this is electric field. What is J? That's why electric field. What is this J? But looking at this equation, this now says what? The cross of H depends on changing electric field plus something called something J.
Sorry.
So it seems like it's switched, right? Before we were talking about a changing magnetic flux density creates an electric field. But now we are saying a changing electric field plus something called J is creating a magnetic field that curls.
So del cross H is a curl.
Curl of H, right? So similarly, before we saw how the electric field curls around a changing magnetic field, right? Or flux density, del B over del T. That's what we saw last time. Okay.
Suppose it's this last term, derivative of
this one.
Derivative of D, if it is not there, then del cross H is J is what is J? Del cross. I know. Electromagnet we were saying, if you send current through a coil, it magnetizes. Just has something to do with that?
Yes. Basically, this is what Ampere said, right? If there's a long wire, for example, you send a current, right? I think what we call the right hand rule, I don't know.
Yeah.
The current direction.
Yeah.
And you have the magnetic flux.
Correct.
Now, you're saying if this is not there. Good point. So J is actually called
current density.
Yes. B conduction. Current density. And this obviously relates to the conventional electric current flow in a circuit. And in ampere per meter squared, correct? Okay. Now what about this changing electric field? How does that work? How can now let's say J is not there. But that means the changing electric field still should be able to produce this changing magnetic field. Let's say
that's not possible.
Just say 0.
Change in electric field produces
a magnetic field.
Magnetic field.
Because let's say J is 0, but you still have this component, right? Because if this was J multiplied by this, then if one is 0, then the other is 0. But you have plus here.
Yeah.
How is that possible?
So that means it has to be some current.
There has to be some current.
Yeah.
Right? Because in the first case, you talk about a current.
Yeah.
Now, here also there must be some current.
Yeah.
So
special current.
So a change in the electric field leads to what we call a displacement current.
Yes.
Now, I think the easiest way to probably explain this displacement current is if you take a capacitor. Okay, let's say you have two plates. It's one plate here, Another plate here. I have a wire here. And here. Okay. Now, let's say you send a current I through this wire. It goes here. Comes up here. Capacity here. Now, as you said, Boby, when there's a current, there's a wire, there will be an electric field here, correct? Oh, sorry, there will be a
Magnetic field.
Okay, let's say B. Now, when you send a current here, if this is two plates of a capacitor, let's say a charging capacitor, and what's going to happen afterward? When you charge the capacitor,
They got charged and positive and negative. Yeah.
yes, but then you also create
Some electric field there.
electric field. Now, this electric field, when you're charging and discharging a capacitor, is changing, right? This change in electric field is what we are referring to here.
Mm-hmm.
And that will also create magnetic field. Even though there is no connection here, right? Here, J refers to your normal current flow in a closed circuit. But here, this electric field between, let's say, positive and a negative plate will create its own magnetic field. Now, that also depends on how fast you're charging and discharging your capacitor.
Mm-hmm.
I mean, for me, this is...
So if it's a sinusoidal current,
Uh-huh.
then the electric field will also be going positive, negative. Okay.
And your magnetic field will also be going back and forth.
Mm. So if the frequency of that current is more,
Uh-huh.
then for the same dielectric material, this component will be higher
Yes.
because the derivative d by dt.
Here.
Ah.
dE by dt.
D by dt of derivative of...
A derivative of
Yeah,
the
yeah.
electric field. Yes.
So because that is higher, it will be higher. So this displacement current is the current flowing through, for example, a capacitor.
For example, I cannot think of any other example. The only way I can explain it is by saying a
That is the current.
capacitor. Now, that's and you know it also shows a nice drives a nice point. It means, as you said before, even though there are no currents flowing conventionally, right? You can still create a magnetic field.
So without this derivative component, that equation was not full.
Yes. So there is some history.
Yeah.
I'm not too sure about this history. I'm not sure if you know, but
Yeah, I think initially it was del cross H is equal to J.
Ampere's law.
Yeah.
Yes.
Yeah.
I
But
mean,
it is not satisfying this condition. That's what you have described.
people were confused.
Yeah. So then they introduced this displacement current component.
So it's a complete equation. So those are the four equations of Maxwell. Right?
Fundamental equations.
Fundamental equations of Maxwell. I think very interesting, right? I think, and I think if you know those equations, when you come to a point where you have to design a sensor or you want to understand how a sensor works, I think it will really help to know these equations.
Yes.
Even though you will not come back and derive
Just say
equations or remember what curl is or divergence is, but it will give you a very solid background or understanding of how electromagnetic sensors work. So as we go along this lecture, I think the students should not have any problem understanding the principles of any other sensors we discuss. Okay, there are many different ways how you can apply this knowledge in magnetic and electric field sensors, but in general, they all obey these four equations.
Yes. And this equation is not just for our sensors, it's for
yeah.
any electromagnet.
Oh, yes, absolutely. I mean, you can get very deep in electromagnets, right? Yeah. So it applies to so many things. Okay, now that we've covered the basic equations, okay, this is again a summary for the students. Electric current or a change in I or a change in electric flux through a surface produces a circulating magnetic field around any part that bounds that surface. We saw that. And the rate of change of this magnetic field, right, is proportional to both the current density and the rate of change of electric flux. Right, so those are the 4 equations.